All right, welcome back. So today is our buffer lecture. Basically, the structure of today will start from like administrative questions on midterm exam, see if you have any general questions I could answer. And then I'll try to re-emphasize what we did at the end of last lecture, because I was a little bit rushed approaching the end of last lecture. So I just want to make sure I do that appropriately before you walk into your midterm exam. And then we'll do some practice problems together, some true and false problems and some more comprehensive type of problems. So before we get started on any of the actual course materials, any general questions for me? Anything you want to know for Wednesday exam? Yes?
Are we going to get an answer key to the practice midterm?
Well, you can, I don't have an answer key, but you can find the walkthrough to that midterm one in the previous YouTube channel.
Oh.
Yeah. All right, so if no more questions, let's just get started on today. So we'll first do a quick review. Basically, let's just have a summarize in what exactly have we discussed from lecture 1 all the way until today, right? So we went over 3 different chapters. In these chapters, we started by defining terms in thermodynamics, right? You learn what's the definition of system versus surrounding, what's a state function versus a line integral, and, well, you have adiabatic processes, isothermal processes. So these are the vocabularies of thermodynamics. And then from these chapters, basically every chapter in 1 to 3, we have one state function relevant to a law of thermodynamics. So these laws of thermodynamics, we just accept them to be true. It's not our job to prove that these laws are correct. So in our chapter 1, we went over what we call the zeroth law of thermodynamics, stating 2 systems that are each found to be in thermal equilibrium with a third system will be found to be in thermal equilibrium with each other, right? So in order to better describe the zeroth law, we define temperature. Or temperature itself is a state function, right? So you can define the temperature of a thermodynamic state. And if 2 systems have the same temperature, you can say they're in thermal equilibrium with each other. So that's our zeroth law of thermodynamics. From there, we also went over discussion of equation of state. So we have equation of state that's telling us what's the relationship of pressure, volume, and temperature for a specific thermodynamic state, for a specific substance. So you can have ideal gases, you can have van der Waals gases, you can have liquid, you can have solid. So whatever you're trying to describe, there always exists some kind of relation between pressure, volume, and temperature. We went over the derivation to show only 2 partial differential equations or 2 experiments are needed to determine the equation of state. So these are experimentally determined equation of state. They're specific to the substance we're studying, like ideal gases, real gases, liquid, solid, whatsoever. So that's chapter 1. And then moving on to chapter 2, we now have a focus on the first law of thermodynamics. Or basically in the first law, we say there exists an extensive state function, energy or total energy, so that for any process in a closed system, we have this delta E equals to Q plus W. Okay, so this one should be, should be delta E equals to delta U plus delta kinetic plus delta potential. And these 2 are 0 if we say it's at rest. No external field. And thus, for thermodynamic purposes, we have delta U equals to Q plus W for a closed system. At rest and no external fields. And also, since we know energy is conserved, we have, well, delta E of the system plus delta E of the surrounding must add up to be 0. So energy is conserved. And then in our first law of thermodynamics, so in chapter 2, we started from the first law of thermodynamics. We have internal energy. We also have enthalpy. So we have H equals to U plus PV. And in the process, we went over how to calculate work and what does heat and work mean. So these are the line integrals. So the most important thing of the second chapter is to know what's the difference of state function versus line integral. Like what's the actual definition of these terms? And what are the properties of these state functions and line integrals? So do some true and false problems later on and see how we can ask questions on these kind of conceptual topics. So that's our second chapter. And then from there, we also moved on to discuss how to calculate delta H and delta U, also Q and W, for different thermodynamic processes. So that's at the end of chapter 2, we did a bunch of derivation, right? So for isothermal processes, how do you calculate reversible PV work? You could use W equals to negative PdV. Or for a cyclic process, you know delta U equals to 0, you know what work is, how to derive Q, right? So these are the general like strategies I expect you to know, which is how to calculate delta H, delta U, Q, and W for a defined thermodynamic process. And then we moved on to our chapter 3, in where we started from heat engine. Right? So the initial idea of the second law of thermodynamics, starting from chemical engineers, want to make a heat engine that's as efficient as possible to translate all the heat into work. Then we went over the derivation of the Carnot principle, stating the reversible cycle as a most effective cycle, using the second law of thermodynamics. And then from there, we built the Carnot cycle, which is a reversible cycle containing 2 isothermal steps and 2 adiabatic steps, all reversible. And from there, we find out there must exist some kind of state function S, whose derivation, ds, equals to dq reversible over temperature. We later generalized that observation into any kind of reversible cycle and define entropy as our state function. And in our last lecture, last Friday and this Monday's lecture went over calculations in how to calculate delta S for different thermodynamic processes. Like, what if it's reversible phase change? What if it's reversible? What if it's irreversible change of thermodynamic state? You can build reversible paths so that you can calculate the delta S of the entire process. In our last lecture, we were focusing on understanding what exactly is delta S. So here's a quick reinforcement on that topic, which is what is the physical meaning of delta S, a little bit slower. So in our last lecture, we went over the derivation of saying entropy itself is maximized at equilibrium. So this one basically is we make the observation, right? So only when reversible processes taking place, the ds will equal to 0 for the entire universe, when only reversible process taking place. And when irreversible processes are taking place, or processes before equilibrium, we have ds larger than 0. Or the other way to put it is if we take the integration, we have delta S equals to 0 for all reversible processes, and we have delta S larger than 0 for irreversible processes. So from here, we then make the hypothesis of, well, instead of, on top of entropy, what else is maximized at equilibrium? And then we use our mixture of ideal gases as an example to derive like what else can be maximized at equilibrium. So in this process, remember we started with your molecule D and molecule E separated in 2 different tanks. Then we remove the partition and allow them to freely move around. Right? So in the middle one, that's right after the partition is removed. And then your gas molecule is going to basically go anywhere it like. And at the end, at equilibrium, this is the highest probability state in which your gas molecules are evenly mixed. right? So we say like this process at right now in the purple one, this is a low probability state, and in the blue one, that's a high probability state. We did some derivation, so on that part of derivation, that one is conceptually important, but I don't expect you to know to get to the conclusion that S equals to K log P plus A, where P here is probability, and A here is our constant. K is also constant. Right. So that's pretty much where I left over. But I want to revisit this problem of actually solving what is the delta S of this mixing process using probability theory, and then compare that result with something that we saw before, which is using the thermodynamic relations, and see what exactly is the relationship of these K and A. What exactly is that constant? How is that related to some of our thermodynamic constants? So let me just write out what we have derived in our last lecture. Using thermodynamics, this is what we find. Where's my chalk?
There's some here.
I have some more. So this is what we find. So this one is my delta S equals to negative number of mole of your molecule D times R times ln the mole fraction of molecule D minus number of mole of molecule E, R times ln mole fraction of molecule E. Right, so remember, this is something we solved using thermodynamic relations. During that process, we were saying this mixture itself is irreversible. So we have a reversible expansion of the volume of your gas into the final volume. And then you have an isothermal mixing of the two ideal gases, right? So the second one is effectively have delta S equals to 0. The first one has delta S equals to this one, and it adds up to be that expression. So that's what we did last time. So now let's use probability and think about it this way. I'm just going to leave the setup there for your reference. And let's see. From this probability of S equals to K ln P plus A. Again, this one is probability. And our goal is to solve the delta S of the process using probability. They should have the same answer. Now, okay, first of all, what do we have? We only have S, right? We only have the actual entropy. And in the question, we're trying to solve for delta S. So what does that mean? We want to write delta S as S final minus S initial, or that becomes this K ln P final minus K ln P initial. Right, so in this process, yes? Well, so we went over derivation of delta S using thermodynamic relations by building the reversible path in our last lecture. And then we went over the physical meaning of entropy being a function of probability, right? But if we're doing the same kind of calculation for this mixing process, we'll have another expression of delta S, and these two expressions will be exactly the same. So we're trying to find out what exactly is that relationship. Now we have some random constant K and A. How are they related to our gas constant? All right, so in here, we simplify this by taking the differences between your two thermodynamic states. And obviously, we find out this constant A doesn't matter because it will cancel out. And for entropy, we're nearly always talking about relative entropy between two thermodynamic states. So that A doesn't matter. That constant will always cancel out whenever we're talking about entropy changes. So that's one observation. And then from here, we can further simplify this one to be K ln P2 over P1. And again, P stands for probability. Well, now we just need to express what is my probability of my final state over my initial state. So first, thinking about my initial state. My P initial, which is, well, you have 1/2, which is 50% of your molecule D on the left-hand side, 50% of molecule E on the right-hand side. So the initial state will be, well, 1/2 to the power of number of molecule D times 1/2 of number of molecule E. So note that in here, we're saying it's even partition. But in your exam or homework, we could easily say it's like 1-3 or 1-4, and these numbers will change. And in this case, we're just saying like, okay, it's even partition. We have the same number of molecule D on the left and same number of molecule E on the right in this question, because we can just count it. So by assuming ND equals to NE, my P initial is simplified to be 1/2 ND. Yes? These two are multiplied together. Yes?
Will the fractions always like be the same? Not necessarily they'll always be 1/2, but would they like be the same, like 1/3 or?
Well, it will add up to be 1.
Okay.
Like they don't have to be the same or not.
Oh, added.
Yeah. So that's our P initial. What about our P final? My P final is our equilibrium state. Or the other way to put it is my P final is almost equal to 100%. Or whenever we say a state is at equilibrium, we can basically say that state is only infinitesimally away from 100%. So it's almost 1 at equilibrium. So taking that together, we end up getting an expression of delta S. So we have delta S equals to K ln 1 over P initial, which is my 1/2 ND. So that's my K ln 1 over 1/2. Wait, this is 2 ND, sorry. 2 ND. Well, it's in the logarithm, it's 1 over 1/2. We can bring it up. We get my K ln 2 to the power of 2 ND, end up getting 2 ND K ln 2. These are just maths, just like moving things around for a logarithm. So far, so good? And now thinking about what do we have on the top? So that's coming from our thermodynamic derivation. What do we know? We know that number of mole of D equals to number of mole of E, and these equals to actual number of mole of D over the Avogadro number. Right, so that's number of mole there. And in addition, we also have my chi D or equals to chi E equals to 1/2, or these are my mole fraction. That's at what percentage you have these molecules. Yes?
Could you just briefly say again why PF is 100%?
This one, we're saying the final state is a equilibrium state. So a thermodynamic state at equilibrium is only infinitesimally away from 100%. It's nearly always at equilibrium, given like infinity amount of time. Like we don't care about kinetics, but thermodynamics speaking, a state at equilibrium state is our highest probability state. All right, so in here, by taking A, that number of mole of D equals to E, and also my chi D equals to chi E, we can further simplify the top equation to be my negative 2 NDR ln 1/2, or you can take this out to become 2 number of mole of D times R ln 2. Yes?
So Professor, like, is like the goal of like this whole problem just to like simplify it to like that final?
Not to simplify, the goal here is I want to ask you, what is this K?
Like,
How is that K related to some of the constants we went over? All right, so what do we have now? So on the top, using our thermodynamic laws, like building the reversible pathways for this ideal gas, we got 2 ND R ln 2. And then using our probability, we get it to be 2 big N D times a constant ln 2. And what's the relationship between your gas constant and this constant K? Now my number of mole, big number of mole D equals to ND times the Avogadro number. Or the other way to put it is we have the K times Avogadro number NA, that gives you your gas constant. Or the other way to put it is our gas constant equals to it's another way to put it is K equals to R divided by NA. All right, so if you remember those universal constants that defining our physical world, right? So one of the basic universal constant we have is Boltzmann constant. Now here, this is our Boltzmann constant. So it's fundamental to thermodynamics, and it is deeply related to the gas constant, which is something you can experimentally measure. All right. Yes?
I'm so sorry. For the calculation, how did you get natural log of 1/2?
This one? Natural log of 1/2, that's just negative natural log of 2. So that's where the negative disappears.
Oh, sorry. When you got it from the thermal.
Well, we know that the mole fraction equals to 1/2, right? So these two molecules have the same number of moles. So the mole fraction is the number of mole of molecule D over total number of moles, so that's naturally 1/2.
Wouldn't it cancel it out because they're the same probability?
No, okay, so for the top one, we don't care about probability.
Oh.
Don't miss yourself, okay? So there are two different ways to solve for the same result, but do not miss them. So do not like mix them together. Yes?
Is this also only for ideal gases?
Well, so this relation is generally true. We just use the ideal gas, the mixing of ideal gases, as an example to demonstrate what is the nature of entropy. Now, if the nature of entropy is true for ideal gases, it will be generally true for any other kind of systems. It's just a calculation is like 10 times more complicated. Yes?
What is
Na is the number of mole of molecule. So in this case, on the left, number of mole of my molecule D is, well, the number of particle on the left-hand side. That's what we are saying. So the big N is the actual number of particles. Small n is the number of mole of the particles. All right. So that's a quick refreshment on what we discussed last lecture. And I hope, like, by now you have a good understanding in what is entropy. All right, so when people ask you what is entropy, what do we know about it? It's a form of probability. All right, and entropy maximizes at equilibrium. That's all. All right, so let's get to some practice problems for your midterm exams. So these are true and false problems you see often in your textbook. These are very educative, I would say. Like these are like kind of conceptually challenging. Like when you read it through, you want to make sure you don't make any assumptions. So in my true and false questions, I'll also make sure like I give you any kind of assumptions I wish you know. Otherwise, do not make any assumptions when working on true and false problems. All right. So let's read it together and see how do we do it. First one, we have delta H is a state function. So whenever you read this kind of statement, you want to go back and check the actual definition of the state function. So if I'm reading that with you, the state function is saying a thermodynamic system in a given equilibrium state has a particular value for each thermodynamic property. These properties are state functions. All right, so a state function describes a specific thermodynamic state. Now looking at it here, is delta H a state function? So raise your hand if you think yes. Raise your hand if you think no. Right, so this one is not a state function because delta H itself is only defined for H final minus H initial. It's not defined for a thermodynamic state itself. It's talking about a difference between initial and final state. So that's the first question. Yes?
Would just regular H be state?
Yeah, H itself will be a state function. It's like if we say delta S, right? Delta S is not a state function, but entropy is a state function. S is a state function. All right, that's the first one. Second one, CV is independent of temperature for every perfect gas. So this one is a little bit tricky. This is why I keep saying like, let's not making the assumption of CV is constant for every ideal gases without knowing like what exactly is the system we're talking about. Like, is it an ideal gas mixture? Like, what's actually in that composition, right? So this is one of those questions. Like, don't answer too quickly to say it's true. Wait, that's B, sorry. Next up, delta U equals to Q plus W for every thermodynamic system at rest in the absence of external field. So again, this is one of the tricky questions because we didn't specify the system is closed. And thus, this is a false. All right, so these true and false questions, they are very conceptual. So whenever you're answering them, try not to rush it through. Try to go to the very first time you see these terms and actually read it through. It's like, okay, in what conditions these are true? Are they true by definition? Are they true for like closed, at rest, no external field, which is our first law of thermodynamics, right? So make sure you're reading the question carefully, think it carefully, and then answer it. Okay, next up, we have D. A process in which the final temperature equals the initial temperature must be an isothermal process. How do we think this one? Okay, anyone think it's true? Anyone think it's false? You want to explain why you think it's false? Yeah. Right, so that's definitely one of the approach, right? We don't know whether or not, what's the steps that's taking. So for an isothermal process, we're saying temperature is constant. Or the other way to put it is we have dT equals to 0. So although your initial and final temperature could be the same, but if we don't know how exactly it's taking place, the temperature can change along the process when delta T equals to 0. Or this is one of the questions that highlights the difference between dt equals to 0 and delta t equals to 0. So delta t only gives you initial and final state. dt equals to 0 also gives you along the entire pathway, your temperature has remained not changed. Okay, and then part E. For a closed system at rest in the absence of its external field, so we're happy. It looks like our first law of thermodynamics is happy. Then we have U equals to Q plus W. So what is wrong with this statement? It should be delta U, right? So it's also false. We're having overwhelmingly amount of force, huh? And then we have F. U remain constant in every isothermal process in a closed system. So this is, well, as long as we didn't say it's ideal gases, we can never know whether or not U is constant for an isothermal process, because U can also be a function of volume for non-ideal gases. So this is another of the iconic example that people tend to miss, is if we didn't specify something as ideal, you cannot assume it is ideal. If you don't know, or if the question is ambiguity, like you can always raise your hand and ask us. Okay, we're happy to clarify it for you, but do not assume something is ideal unless we specified it to be ideal. Yes?
Would it be true if it was so if it was an ideal gas, then it would be true, but does the U have to be a delta U as well, or can it stay?
So this one, we don't have to, because U is only a function of temperature, right? So if your dT is not changing, then your du is also not changing, right? U is a function of temperature. So for ideal gases, then it will be true. All right, next up. Q equals to 0 for every cyclic process. This one is kind of obvious, because this one is false, because my Q, or heat, is a process-dependent function, or a line integral, so it's path-dependent. And then let's look at H. Delta U equals to 0 for every cyclic process. True? False? Yeah.
I want to say true because I feel like because like.
Yeah, it is true, right? Because it's a state function. So, I mean, delta U equals to 0 for every cyclic process. As long as it is a cyclic process, by definition, we know it has the same initial and final state. So delta U must equal to 0. Same applies to delta H and delta S, or delta T, delta V. So if it's cyclic, your initial and final thermodynamic state are exactly the same. Yes?
And then what about, well, this kind of goes back to like the isothermal question, the delta U, that's true equaling 0, but then du?
This one, no, because only for ideal gases, you know how your internal energy changes with temperature. For a non-ideal gas, your internal energy is also a function of volume, so you don't know how your internal energy is going to change with respect to temperature. All right, next up. Delta T equals to 0 for every adiabatic process in a closed system. So this is one of those questions, is asking you to get familiar with these vocabularies, right? So delta T is talking about change of temperature. Adiabatic is telling us Q equals to 0. Now, Q equals to 0 doesn't necessarily mean your delta T is 0. We went over the derivation of you can have expansion of gases where your system is doing work on the surrounding. And so delta T can be 0, but you need heat input. Or in this case, we have adiabatic, and then for reversible adiabatic processes of ideal gases, remember we derive like T2 over T1 equals to V1 over V2 R over CVM, right? So it's not. Question J. A thermodynamic process is specified by specifying the initial state and final state of the system. So think about it. What is a thermodynamic process? Like the one we just did, right? So for adiabatic process, only knowing the initial and final state, is it good enough to identify an adiabatic process? Obviously not. right? So you want to know what the path is. So for this kind of question, you want to think about, okay, so let's say a thermodynamic process is specified by specifying initial and final state. So let's just imagine any kind of thermodynamic process, like adiabatic, isothermal, whatsoever. And you'll find out all of them defines like some kind of limitations along the pathway. So not only the initial and final state. And some of these questions are effectively the same question, just different wording. Okay, next up. If a closed system at rest in the absence of external field undergoes an adiabatic process that has work equals to 0, then the system's temperature must remain constant. I'm going to highlight it for you. Any thoughts? So let me just write down what I think when I'm reading this question. Now, a closed system at rest in absence of external field. Okay, so reading it, I know my delta U equals to Q plus W, my first law of thermodynamics. It undergoes an adiabatic process. Okay, so we have Q equals to 0 and work equals to 0. So from reading the sentence, we know my delta U equals to 0 for this system. But then it says the system's temperature must remain constant. So do I know about temperature? And I don't, right? Because we didn't specify it being an ideal gas. So I don't know how my internal energy is going to change with respect to temperature. So this is what's going on in my mind when I'm reading this kind of question. Like every time you encounter sentences, you translate it into equations that we went over in class based on those conditions. And then things become quite obvious. And that's false. Next up, PV work is usually negligible for solid and liquid. Yes?
Quick question. So when you say that you don't know how U is dependent on T just because it's ideal, is that because in a non-ideal gas it's also dependent on the volume?
Yeah, that's it.
Okay, so if it were to say like both temperature and volume or something, then it would...
Well, if your temperature and volume are both held at constant and you have equation of state that's holding a relationship between Tp and V, do you really have a state change? Right? Then you'll have the same initial and final state, then delta U obviously equals to 0. Yes?
If it was for an ideal gas, would it also still not be necessary?
So for this one, if we specified ideal gas, then it will be true because your internal energy is only a function of temperature.
Wouldn't it focus only on the change in temperature? When its temperature rises?
Well, so in this case, you have delta U equals to 0, or actually du equals to 0 throughout the whole process because your Q and W are both 0, right? So in this case, your internal energy is equal to 0. For ideal gases, temperature equals to 0. All right. And, well, next up, I'm actually going to skip the rest of it because the rest of it are more or less just math. Like some of them are just like doing the integral calculus so that you can know like what's going on there. I have like about 10 minutes. I want to show you different format of problems. So these kind of true and false, I shared with you like what am I thinking when I'm working on it. I also posted my way of thinking in our annotated note. So go back and try it yourself and see what you get from it. And now let's look at a more like comprehensive style of question. So this question is one of those things that when you first read it, you'll feel like, okay, this is an unfair question. We didn't go over this cycle in class. But you actually have everything you need in order to solve this problem. So let's look at it. So we went over Carnot cycle in class. In class, we went over Carnot cycle, being a cycle consists of 2 reversible isothermal processes, 2 reversible adiabatic processes, right? So remember we did the assignment of Q, W on the board together. We also know that efficiency of any heat engine, that's defined as your W over QH, the absolute value of W over QH. Or the other way to put it is your heat engine is absorbing heat from a hot reservoir, transforming that heat into work. And efficiency tells us how much work comes out from that QH. So in this question, if we're thinking about a different kind of thermodynamic cycle, which in this case is called Brayton cycle, so this cycle is actually used a lot in engines for your jet flight. All right. And looking at it, how it is being set up, we have on the left, we have an inlet, and on the right, we have a nozzle. And in here, you have compressor and turbine. So in here, we're saying, in my two closed chamber of compressor and turbine, we have ideal gases in there. That's telling you. And this cycle go like this. We start from a reversible adiabatic compression of this inlet of the compressor. So basically, we're compressing whatever in there, compressing the gas inside the compressor. So that's our first step, from A to B. So that's an adiabatic, that's a reversible adiabatic compression, or volume is going down. All right, during that process, it's adiabatic, volume going down, your pressure is increasing. Next up, from B to C, we have an isobaric heat input. We didn't specify it being reversible though. So in here, we're just saying there's some kind of heat input to my cycle. Likewise, probably you have some kind of fuel burning in the combustor, and that heat got transferred into your compressor. So in here, on the figure, on the PV diagram, what we're getting is the temperature of your point B increase to some point C from an isobaric fashion. And then from C to D, we have the reversible adiabatic expansion. So after my gas absorbs heat at that constant pressure, now release that pressure restraint and allow it to expand. And in this process, we have the reversible adiabatic expansion, and your compressor go back to its original state, and also output work through your nozzle. And finally, we have D to A, which is the isobaric cooling. We, again, keep the pressure at constant and cooling the system down to the initial state. But one of the things we can ask you is, let's say, I remove this A, B, and C label on the figure, and I tell you what is going on, like A to B, B to C, C to D, D to A. Ask you to give me the labels on the figure and tell me what's my A, B, C, and D. That's one way I can ask you. Or I can give you the figure of A, B, C, and D and say, I'll tell you these two are adiabatic. I might ask you to describe to me what is going on between B to C. So there are different ways we could ask you. But for this question, we're saying, I'm telling you everything. I'm giving you the figure. I'm telling you what's going on. Now, can you calculate the efficiency of the cycle? And assuming we have constant Cp and Cv for ideal gases in my nozzle. And I want you to express your answer into A, B, C, D, 4 different temperatures on the figure. All right, so I'm going to do that on the board with you. So first of all, what do we know? We know that in this case, when we're talking about my system being my compressor and my turbine, we have my closed, non-isolated system. Well, again, we can assume it's at rest. The entire system is at rest, and also no external field. So if we're looking at the entire cycle, well, we have delta U equals to Q plus W. Or if we're looking at my delta U of my entire A, B, C, D, the change of my internal energy must equal to 0. So far, so good. It's pretty straightforward, right? You read the question, we say you can use the first law of thermodynamics. You have your first law of thermodynamics. You have the cyclic process, delta U equals to 0. What else do we know? Now, we also have my delta U equals to Q plus W. So we want a relationship between my heat and work. Now, looking at the figure, what do we have? So in process B to C, remember we have the combustion. We have the combustion of energy input into my system. That's our B to C, which is my isobaric heat input, right? And then from my D to A, that's my isobaric cooling down. So in two processes, we have Q1 and Q2 associated with it. Now on the figure, you can also read it to say like here, we have our Q2, and here we have our Q1. So Q2, total heat equals to Q2 plus Q1, where Q2 is this heat flow into the system. And my Q1 is my heat, the system to the surrounding. And since my delta U equals to 0, Q plus W equals to 0, we can write my W total equals to delta U minus Q2 plus Q1 equals to negative of Q2 plus Q1. Right. And in here, the W total, we're talking about the work that's being done out from the system. So that's the amount of work your system is doing on the surrounding, and that's why it's a negative number. Or since we're talking about the efficiency, we want to know how much work, what's the absolute value that's being outputted. So we also can put that as your absolute value. Yes?
Should it be Q2 minus Q1 in the expression if you're taking the negative out?
All right. And now let's think about the two isobaric processes. So since the question wants us to express our number in temperature, in the change of temperature, and we only have my Q2 and Q1, we want to translate that Q2 and Q1 into temperatures. So how do we do that? Well, we have isobaric. We have ideal gases. So what do we have? We have my QP equals to delta H. And for ideal gases, this equals to Cp delta T. And we also assume like Cp is constant, right? So in this case, we can then rewrite our Q2 and Q1 into delta T. So my Q2, that's the B to C. So my Q2 equals to Q, B to C equals to Cp times Tc minus Tb. And here is when we can do a quick sanity check. Now, we're talking about a heat capacity, which is a positive number, times Tc minus Tb. So for ideal gases, we know that Tc is going to be higher than Tb. So we're expecting my Q2 being a positive number. And that fits our expectation because Q2 is the heat input between your process B to C. And that fits our expectation. It's like a sanity check. And if it's in an exam, the first question we could ask you is predict what is the sign of Q2, QB to C, and also QD to A, right? And later on, you'll see, okay, they match up. And same applies to Q1. So my Q1 is a QD to A. That equals to Cp Ta minus Td. And you look at it, you'll be like, okay, TA is smaller than TD. So this is expected to be a negative number, and so it is, right? It's the output of heat from your system. And now we have our final efficiency. That equals to your absolute value of work over your QH, which is your input. Right, so the absolute value of your work is Q1 plus Q2, and your QH is just this one. And we can write it out. On the top, we have CP and TC minus TB plus TA minus TD divided by TC minus TB times CP. And my CP cancel out. It's only a function of your 4 temperatures along the cycle. All right, so this will represent one of the comprehensive kind of question. It involves multiple parts, but everything we used here, we discussed in class. All right, you'll also see my derivation on the annotated note. I also have more true and false problems for chapter 3 in the rest of the buffer lecture, so if you have time, do check it out. And I have office hour tomorrow, so that's it. Good luck. See ya.